Okay.
Okay.
So slide 1, we can skip. Slide 2, big brain theory. I just, if anybody recognizes me, I was on Big Brain Theory as a Science Channel or a Discovery Channel show a couple years ago. I'm also on the Science Channel, Outrageous Acts of Science, so you can see me there. I like to share that because some people like wonder. Okay, so slide 4. So let's go ahead and skip to slide 4. It says 1986 3D systems. Got it?
Yeah.
Okay, so 3D printing was actually invented way back 30 years ago in 1984 or 1986 by Chuck Hull. And Chuck Hull was actually a photoresist chemist or something. Like he was working with photoresists on circuit boards and that kind of thing. And he realized that if he could cure this photoresist, but if he added more on top of the layer that he was doing, because they would just cast them in thin films, he could selectively cure with a laser, and he could add layers together. And he's like, well, if I kept adding layers, I'd have a 3D part. And so that's how 3D printing was born. It was way back in 1986. So there's actually been several rebirths and deaths of 3D printing, and it all started with this. So it came out as huge. People were super excited. You know, it's the first they'd ever seen a 3D printing. But the problem with the technology at that point was that photoresists were so fragile, and the material properties just were not good. You'd hold the part in your hand and you think, oh, this is going to change the world. But then you set it on your desk and you come back a week later and it's slumped over. So at that point, everyone's like, okay, this is not going anywhere. So it kind of died, came back to life. Let's go to slide 5. 1995, the ZCore indirect 3D printing was invented. And so this is a powder-based process. So just like the metal powder that we saw, you spread a layer of powder, and then you take an inkjet print head and you deposit a binder into that powder bed. This was really exciting because now you could do full color. So just like your inkjet print at home could do full color, this can do full color 3D prints. And so this was the second rebirth. So there's a bunch of hype around 3D printing, and everyone's like, okay, now it's going to change the world. But the problem is that you hold these parts in your hands and they crumble. They're very, very fragile. No real mechanical properties to speak of. And so then again, we're like, the world is like, okay, this is not going anywhere. The original ZCore process is a starch-based powder and like a sugar-based binder. So, you can see how fragile it is. And it's interesting, it was actually invented as a party trick. Some MIT student figured out that he could 3D print sugar cubes for tea or something. And so anyway, that's how it was born. On the sidelines, going to slide 6, a company X1 bought the patents to the MIT technology, and they started printing a binder into a metal powder bed. And, glued together metal powder, that's not useful. But as you could see from the part that I clanked together earlier, if you fire those printed metal parts, so if you put that printed metal part into a furnace, you can center and infiltrate it and make it a fully dense metal part. So that's been going on in the background. It's actually, 25, 30-year-old or, probably like 25, 20-year-old technology, and they're a very well-established company in this technology. So that was going on in the background, but still, no hype behind that. Let's see, go to slide 7. 1989 was when fused deposition modeling first kind of started. They originally called this rapid prototyping. But through the years and towards I guess probably about 6 or 7 years ago, people started realizing that you could use this technology. This is like the MakerBot technology, the desktop 3D printer technology. This is when you're taking a string of plastic and you're feeding it through a roller through a hot nozzle. So it's just like a hot glue gun. If you took a hot glue gun and you drew a square, you let it cool, draw another square on top, and you kept drawing squares on top of each other, you'd have a 3-dimensional cube. And that's how fused deposition modeling works. And so it was about maybe 6 or 7 years ago that people started realizing, hey, this is not just for prototyping. These polymers that we're using on this printer are just as good as the polymers we use in injection molding. And in fact, we use the same polymers. We use ABS, which is like a polystyrene kind of thing. But ABS plastic is what's used on most things that are plastic, and you can extrude those through a nozzle and get really great material properties. So it was about 6 or 7 years ago that it really started taking off. Go to slide 8. Big companies in plastics. So these companies have been growing over the years as the technologies have developed. Stratasys is one of the major ones. They own MakerBot. They bought the MakerBot patents. They own Objet, which is another inkjet type of technology. And then they have that big machine that you saw with Brad in front of it. That's a Fortis, and that's a Stratasys machine as well. So they have a really great selection of FDM platforms for the industrial and for desktop. And then there's 3D Systems. They bought ZCore. They're kind of like, the contender there. They also have a really great little fun printer called the Cube printer. I really enjoy that printer. It's a great one for education or just at home. But anyway, they have their own kind of technology suite there. So all of these plastics companies have been developing. So go to slide 9. And so as the laser and electron beam technologies have evolved, so lasers used to be like super duper expensive. But as they started getting more and more affordable, they started using them in 3D printing or additive manufacturing. Originally, they were making nylon parts, but they've gone since to metals, and we've been doing metals for probably about a decade. So we've got two in metals. There's the laser, and there's electron beam, and then there's the binder jetting or the indirect 3D printing. So the main brands for those are Renishaw, EOS, Arcam is the brand that we use, and then X1 is the one for indirect 3D printing, just to give you kind of a scope of the different companies and who's out there and who's actually selling products and 3D printing. Sorry, this is going really fast. I do want to share with you some principles of additive manufacturing. So let's go to slide 10. Okay. So principle 1 is that complexity is free. All right. So with traditional manufacturing, I take a block of material and I carve away at it until I get the shape that I want. And the shape I can get is limited to what angles and how long and where I can physically get my carving tool into the part. With additive, it's complete opposite. So I have access with additive to every layer of the part. So if you can imagine this is a crazy looking part, right? If you can imagine this sliced into layers, each one of those layers is just a few dots or a few like ovals. It gets really, really simplified when you slice it into layers. And so the machine doesn't really care what shape I give it for the most part. So with additive, complexity is free. So now we have the freedom to design geometries in basically whatever geometry you want. So you get into the field of topology optimization, which means I have a given load I need to support. What is the perfect structure I need to support that without any waste in weight, without any extra material? So that's really a new field of development that's coming forth just because of additive manufacturing. Okay, let's go to the next slide, slide 11. Principle 2 is variety is free. So traditional manufacturing says that if I have a widget that I produce on occasion, if I'm out of that widget and I need to make more, I have to set up my whole production line, all the tooling, all the calibration. I have to set it all up again to make that one widget. And if I just need 5, too bad. I'm making hundreds of them, because if I'm going to spend the time to set up my production line, I'm going to make a bunch of them. And so now that I've made a bunch of them, I'm going to ship off the 10 that I needed, but then I have to store the rest of them. So there's a lot of waste in traditional manufacturing just because you have to set up your line, you have to set up your tooling, and then you have to store your excess production. With additive, I don't have any tooling set up. I can put all of these parts that you see here in this slide, I can put all of them into one printer and print them all at the same time. So I can do batches of dissimilar parts, no need for setup changes. Principle 3, next slide, slide 12. Principle 3 is that there's no assembly required. So like we saw with the titanium prints and those planetary gear sets, we saw that if I get the clearances right, I can make something like this bike chain. Now, this is a plastic bike chain. I wouldn't put this on my bike. But we can make things like this bike chain where we no longer have dozens and dozens of little parts and pieces to put together. We can just print them all in one assembly and really save a lot of expensive time. On that same note, we can simplify designs that are multiple pieces. So air ducting here on the lower right corner, air ducting is a really great example of something that's doesn't need to be that complicated, but is. If you've ever seen air ducting, you know it's a bunch of bent pieces of sheet metal held together with lots of little fasteners like rivets and stuff. And especially in aerospace, it's a huge burden in terms of like logistics to procure all of these pieces, get it all assembled properly. So it's a big nightmare. So air ducting is a great example. This is actually an air duct that's been 3D printed into one piece. So instead of dozens of pieces, we have one piece. And this is actually flying on some fighter jets right now because it saved them so much money making them this way, so much money and time making them this way, and it's not a load-bearing member, so they don't necessarily have to worry about the material properties. So principle 3 is no assembly required. Next slide, principle 4. Again, like we'd said with principle 2, there's no lead time. I don't have to set this printer up for each different build. The printer is, as long as I've reset it, I've set it up for whatever I'm printing. So there's no special lead times for different parts. Principle 5, next slide. Zero scale manufacturing. Now, this is one of those where it's like, okay, we're not there yet. But the idea is that eventually these printers will be smart enough and just the process itself is flexible enough. You know, we're just doing layer by layer. The printer doesn't necessarily need to be aware of everything that's going on or have to do that much planning. We eventually will get to the point where we can, and we can on some systems, but you know, we want to get to the point where we can just hit the print button and leave, and the printer does its job. So eventually we will get there. It's just a matter of time. Next slide, principle 6. Principle 6 says there's zero constraints. So just like the first principle stated, complexity is free. We also have very few constraints in terms of ideally materials. We're not there yet, but the processes themselves will eventually be universal to any material, any geometry, and we won't be constrained by our typical manufacturing processes and the materials that they use. Next slide, slide 16. Principle 7 is that we have compact, portable, affordable manufacturing. So now we're talking about the situation where I personally have like 3 3D printers at home. Eventually their manufacturing may become crowdsourced where, you know, I have a local business, they need, you know, X number of widgets the next day. Maybe they'll ask me to make 10 for them the next day, you know, and send it to them the next day. And maybe they'll ask somebody else to make some. And so now they get into cloud manufacturing where you're using your local network of these compact manufacturers to supply your product. So it's just a kind of an interesting thing to think about. Principle 8, next slide, less waste. So in all of these processes, we use so much less material than traditional manufacturing. Most of them, we just use material where we need it, not where we don't. So you can see here, these turbine blades are being repaired. This is actually how GE repairs a lot of their non-aerospace turbines that are kind of like low rotation speed turbines. They cut them all off at the same length, and then they add the material back on when they're worn. They add the material back on like this. So we've actually done a study on buy-to-fly ratio for aerospace. The typical buy-to-fly ratio, meaning how much material I buy versus how much I actually end up flying, is like 33-to-1. So if I buy 33 pounds of material, I end up only flying 1 pound of that. The rest of that gets carved away and, you know, recycled as shavings. With additive, it's about 1.5-to-1. So it's almost a 1-to-1 ratio for how much material I buy to how much I fly. So it's a huge material saver because we're only putting material where we need it, not where we don't. Okay, next slide, slide 18, principle 9. We didn't talk about the other inkjet process, but we have a process where we can actually deposit a photopolymer just like with the SLA technology. but deposit it using inkjet. And the great thing about inkjet is you can do multiple materials really easily. So just like your inkjet printer at home can do different colors, we can deposit multiple materials. And so if we use our bitmap then to kind of change the gradient between these two materials, we can do all of these crazy kind of topologies between dual materials or, you know, tri-materials or whatever. We have a lot of flexibility in terms of combining these materials. And now we have these material systems that you could have never made with traditional manufacturing, and they can be super high performance when you combine them in this manner. Okay, last principle, principle 10 is precise replication. In using 3D scanners, you can actually replicate lots of things. 3D scanners aren't that awesome, but you know, we do have the ability to just kind of copy things now. You just take a 3D scanner, you scan it in, and then you put it in a 3D printer. So that'll become a big thing in the future, how we're going to protect against that. How are we doing on time?
Big time.
Huh?
You're
good?
fine.
5 minutes? Okay. Okay, so next slide, slide 20. Of course, a great application for additive is prosthetics or anything medical, because all of our bodies are different, and you know, you can easily change the digital model to fit, you know, to fit whoever's body. So we have this prosthetic here on the left. It's a veteran's prosthetic, and the thing about prosthetics for veterans is that, you know, they typically are ashamed of them and they want to hide them. They're ugly. Well, with additive, they can actually have some you know, input into the design, and they can actually have something really cool, and that turns their prosthetic into something that they're proud of and want to show off, which is a really great thing for their psychology coming back from war. Also, this man and this gentleman in the middle, he's had a disease that, you know, he was missing half of his face. With 3D printing, they could 3D scan the good side of his face and then mirror that and replicate that on the other side of his face using 3D printing to have a really nice prosthetic. And then on the right, prosthetics for kids are really difficult because kids grow really fast and they're usually really heavy and they don't want to wear them. So this is a prosthetic developed by a woodworker, I believe. And anyway, so it takes advantage of, like, if the kid still has a wrist bend, they can latch this thing onto his hand and he can use his wrist bend to actuate the fingers of the prosthetic. Next slide, slide 21. Another application is medical, as you know, if you've ever had a cast, you know, it's like really itchy and sweaty and gross. They can make you a custom cast with 3D printing that doesn't have that issue anymore. You can get it wet, no problem. Also, Invisalign braces, if any of you know somebody or has had Invisalign braces, they actually exist because of 3D printing. They don't 3D print the brace itself, but they 3D print the positive of your teeth, and then they use vacuum forming to form the brace out of a sheet of plastic. So that's actually how they are able to 3D print, or that's actually how they're able to send you a new Invisalign brace every 2 weeks, which is pretty amazing. And then also with skull repair, we can print titanium, and that's, you know, you can put that in your body. So if somebody's had skull damage, like in war, you know, you can scan the good side of the head and scan the hole and then make the perfect replacement for that missing piece. Next slide, slide 22. I'll just touch on this a second, but with binder jetting, we can also print sand. So we were printing metal powder before, but now we can actually also print sand, and it's absolutely revolutionizing the sand cast industry. Casting is a huge industry, but a lot of it's gone offshore to China. This is one strategy that we want to use to bring it back to the U.S. But the hard thing about sand casting, is that you have to make the shape of your thing in sand, and you have to be able to get that shape out. And there's certain things you just can't do because of the way they process it. With additive, we can just print the sand directly without the need for a pattern and cast straight into it. So really reduces the lead time there. Okay, next slide, slide 23. So you saw briefly the manufacturing demonstration facility. That's where I work. We're part of Oak Ridge National Lab. Our two main focuses right now are additive manufacturing and carbon fiber. Next slide, slide 24. My group actually started as a robotics group, which is pretty cool. And they started using additive more and more. Additive is really great for robotics, obviously, because robots are complicated. They've got all these intricate pieces. They're custom. They're low volume. And so it's really great, a really great application of additive manufacturing. Next slide, slide 25. You may have seen this. It's on the cover of a mechanical engineering design book, I think. But this is my boss, Lonnie Love's hand. And it looks really cool. The hand itself has got that mesh, low density structure on the outside, which we could do with the electron beam. But what you don't see on the inside is that all of the hydraulic lines, so this is a hydraulic hand, all the hydraulic lines are already plumbed into the print itself. So instead of making this a very complex assembly that may have not been actually feasible, you print all of these passageways into the hand itself and then just assemble the rest like that. So anyway, really cool application. These are the kind of applications where we look for, not the ones that you can make with traditional manufacturing, but the ones where you can't make it any other way. It's called a high performance geometry, a geometry that's got high performance, you can't make it any other way. So next slide, slide 26. So I talked about bias flat ratio. So you can see this bracket here. This bracket is machined out of one block of material. And you can see that the bracket is very, very low amount of material, but you can imagine how much was carved away. So again, with additive, we're able to reduce that buy to fly ratio, save a lot of material and energy. Next slide, slide 27. So big area additive manufacturing is that big machine I showed you. This is one of our most exciting projects in the past year. It's just a giant maker bot. It's got a huge extruder. You can see there with Pete and Randy there in the picture. It's got a huge extruder. It uses pellets, so it's not using a film anymore. And it absolutely just blasts material out. Go to slide 28. This is a top-down view of the process. A couple years ago, they were printing a car with a company called Local Motors. So slide 29. This is the car. It's called the Strata, which is Italian for layered, which is really cool. Anyway, this is a functioning car. It's an electric car. They printed the whole chassis in one piece. They bolted the fenders on, and they bolted wheels and a motor on. And it was really simple, very cheap, very quickly. And actually, Local Motors has a manufacturing facility just maybe a mile from us, where they're going to be making custom cars like this, custom other large objects with the BAM technology. Next slide, slide 30. This is kind of our version of the Strata. We wanted to do something that demonstrated more of Oak Ridge's capabilities. This is 3D printed. The shell of the car is 3D printed, but it's been obviously buffed and painted to look like a normal car. But the frame was printed and the shell was printed, and then all the rest of the parts were stock parts. It's a Shelby Cobra, so it's a kit car. That's why we chose it. So we just buy the parts and put them on. But it's got a custom battery pack that was developed by our battery lab in our facility. It's also got a custom electric motor developed by our engines group. It's got a lot of other Oak Ridge technology, so it really is Oak Ridge in a car. So it's one of our pretty exciting technologies. Next slide, slide 31. It all goes back, though, to a simple little Solid Doodle desktop printer. I don't know if you've ever played with a Solid Doodle. They're personally my favorite. It's really unfortunate the company's gone out of business. But anyway, we found that in these open air printers, if you don't have a heated oven on FDM, your part's going to curl, and that's a problem, especially on a large scale. And with these large scale printers, we don't have the luxury of heating the chamber. So we just had, we had this huge problem with ABS curling as we're printing. So you can imagine printing a layer, and as materials cool, they contract. So you have a layer cooling, contracting, another layer on top cooling and contracting. So you just build up all this thermal stress. But we tried this one material, carbon-filled ABS, which is the black material, and found that without a heated chamber, it did not warp at all. And that's actually the success behind the BAM system. Without that material, it wouldn't have worked. It just warped way too much. So you'll notice anything that comes off the BAM nowadays is black, and that's because it's got that carbon fill in it. So with that, I don't want to run over time. I can go another 10 minutes or so, or I can stop here.
I have just one quick one. The linkage between the MDF and Local Motors, what's the collaboration you have in between?
Yeah, so we do cooperative research with them. They're developing their facility, but they're coming to us for understanding of the BAM process, and they'll be licensing our technology. They'll be buying these printers, and so we're just basically working together to help them be successful, just helping them however we can.
I was gonna see, how might we be able to tour the facility? Like, I know it's a demonstration facility, so how might we be
Yeah.
able to come over and see some of the stuff you got?
Yeah, you guys can come anytime. Just contact me. I'll get you in touch. We give tours all day, every day. So you're more than welcome to come. Just organize a trip and we'll get you in here.
All right, thanks.
Yeah.
Thank you, Dr. Elliott. We'll be in touch
Yes.
with you. Thank you.
Okay, great. Thanks, guys. See ya.